We had some previous videos on group homomorphisms, and now we go back to the same concept and we will take it a bit further. So we immediately start with the definition of group homomorphism. A homomorphism, let's call it phi from a group G to a group G bar, is a mapping. So you have G here and G bar here, and phi is this mapping from G to G bar, and phi preserves the group operation, meaning phi of AB equals phi of A, phi of B. Let me be more explicit about the operations here. Imagine you have one group here and an operation, and you have a G bar, a group bar, and an operation prime. Okay, so this group homomorphism phi will take from G operation to G bar operation prime, such that f phi of A operation B, so this is this operation, right, equals phi of A operation bar. So this one is this operation and this one is this operation. Okay, phi A operation prime phi B. Okay, so so now we get into the definition of kernel of a homomorphism. So the kernel of a homomorphism phi from a group G to a group with identity E is this set. X will be in G, such that phi of X, so all the images, will be the identity. Okay, so the kernel of phi, a kernel is the kernel of phi, okay, is denoted kernel of phi. Okay, so here you have phi, a homomorphism, so the kernel will be the set. Here you have the identity, so it will be the set of all elements where this is X, X1, X2, X3, and phi of X1 will be the identity, phi of X2 will be the identity. So all these elements here, the image is the identity. So the set of the elements where all the image is the identity is the kernel of the homomorphism. Okay, very first example. Any bijective homomorphism is an isomorphism, and I'm talking about this because if we have two groups, G and G prime, and if phi is a homomorphism but a bijective homomorphism, meaning the homomorphism is one-to-one and onto, so this homomorphism will be an isomorphism. And what's so special about the isomorphisms? The kernel, so the set of the elements that will be mapped into the identity, the kernel of an isomorphism is the identity. Okay, so if there is an isomorphism, there will be only phi of the identity into the identity. Okay, second example. Let us say we have an homomorphism from the general linear group of matrices 2 by 2 with entries in R, mapping into the positive real numbers or non-zero real numbers, of course under multiplication, okay, and here under the usual multiplication. So the mapping will be phi will map any matrix into the determinant of the mapping of the matrix. Okay, so this is clearly a homomorphism from the general linear group dimension 2, entries in the reals, to the non-zero real numbers. Okay, so what is the kernel? If we have here the non-zero reals, and here we have the general linear group, the identity will be the special linear group dimension 2 and entries in R, and they will all map into the identity of this group, the multiplicative identity, of course, because this is reals under multiplication, non-zero reals under multiplication. Okay, so all the special linear group will be, so the kernel of the general linear group is the special linear group. Another example, imagine we are mapping the non-zero reals okay, phi maps the non-zero reals into the non-zero reals. Okay, but it maps such a way that phi will take x into the absolute value of x. Okay, so we have the non-zero real numbers here too. Every single number here, for instance -2, will end up here in 2, right? Because that's the absolute value. So what is the kernel here? So what will the kernel of phi will be? The kernel will be 1, because 1 will take to 1, and -1, right? -1, absolute value of -1, it will be 1 too. Okay, so this is phi, the kernel of phi will be -1 and 1. Oh, let me go back here. I made a mistake here, right? I'm thinking about this now. The kernel, it's not the kernel of the kernel is the kernel of, I'm going to do it in red, the kernel of phi. The kernel is of the homomorphism, not of the okay, of the group, the kernel of the homomorphism. Okay, so in this case would be the kernel of the determinant, right? Because phi, the homomorphism, is the determinant. So the kernel of the determinant is the special linear group 2 by 2 with entries in R. Okay, another example. Let us say we have the polynomials, the group of all polynomials with real coefficients under addition. Okay, so the group of all polynomials with real coefficients under addition. So let us say f is in R, okay, and let us denote f prime, the derivative of f. Okay, so what is the map that takes f to f prime? Well, this is a homomorphism, right? A homomorphism from the group of the polynomials to itself, right? So the kernel, what is the kernel of the derivative? What is the kernel of the derivative? So we have functions here, and here we take the derivative. So we have function 1, and here we have its derivative. Function 2, its derivative. So question, what is the kernel? Well, what is the identity here? Well, we are talking about addition, right? So what is the addition? F plus 0 equals f. So the identity will be 0. Okay. So what are the functions f3, f4 that if we take the derivative we will get 0? The constants, right? So any function that is a constant, its derivative will be 0, right? So the kernel of this application, I'm going to say the kernel of the derivative is the set of all constant functions, right? I hope when I'm watching this I am pleased with my notation. That doesn't happen that often. Sometimes I'm very unpleased with what I see I have done. Okay, and a last example. The mapping from the integers to integers module n, the mapping phi of m equals r, where r is the remainder, of m when it divides n, the remainder will be r, so it will be the remainder of the division of m by n. So m divides n, we will get q, so it will qn plus, Qn, yes, Qn plus R plus the remainder here. Okay, so the mapping of phi, this phi mapping from Z to Zn, defined this way, where this R is the remainder. This is a homomorphism, and you can check that the kernel of this homomorphism is N. This is this is very important. So this natural homomorphism phi from Z to Zn has many applications in number theory. So in 1770, the famous Lagrange proved that every positive integer can be written as the sum of 4 squares, meaning any positive integer can be written as a squared plus b squared plus c squared plus d squared. Okay, every positive integer can be written as the sum of 4 squared. Okay, but that is true, but now we are going to prove that there are infinitely many integers that are not the sum of 3 squares. So, for instance, no integer equal to 7 modulo 8 can be written in the form a squared plus b squared plus c squared. So, no integer, I'm going to repeat, no integer equal to 7 modulo 8 can be written in the form of a squared plus b squared plus c squared. If this was true, then there will be a 7 that would be equal to a squared plus modulo 8, okay, plus b squared plus modulo 8 plus c squared. Okay, but observe that the square of every of any integer either is 0 or 4 modulo 8, of course. The square, the square of any even integer. Okay, do not forget we are working modulo 8. So the square of every even integer will be 0 or it will be 4. I'm going to take this 8 out of here. Okay, that's the square of all even integers. And the square of, the square of the odd integers, it will be 1, right? Okay, so square number modulo 8, you only have 0, 4 and 1. Okay, but none of these 3 numbers, no combination of these 3 numbers add up to 7. Okay, modulo 8, of course. Okay, and that proves the result. Okay, let me give you a quick example of something that is not an homomorphism. Imagine, for instance, the mapping from the real numbers, for instance, all real numbers under addition to itself, real numbers under addition. Okay, and let us say that phi takes x in the real numbers and takes it to, for instance, this one, the greatest integer less than or equal to x. the greatest integer less than or equal to x. Less than or equal to x. You can check. This is not a homomorphism.